In today's class, we'll deal with the pure bending, like bending equation, or you can call it as Euler-Bernoulli's beam theory. So before we start with this, let's see, just we'll look at the syllabus, what we have. We'll look at the syllabus, what we have for our third semester mechanical engineering, mechanics of materials. Okay, if you see here, like for mechanics of material in module 3, in this module, here we have stresses in beam. In stresses in beam, we need to deal with the bending and shear stress distribution in rectangular I and T sections of beam. So if you want to understand like what is the bending and shear stress distribution in rectangular T and I section, I should know the bending equation for a beam, that is M by I is equal to sigma y by y is equal to E by R. So if I know this equation, then I can go for these. Like before proceeding with this model, stresses in beam, I should know what is pure bending, what are the assumptions made in Euler-Bernoulli's beam theory. We'll discuss those first, then we'll go for the bending and shear stress distribution in rectangular I and T section. So first we need to understand what is pure bending. So a beam is said to be in pure bending when, for example, if you have a beam like this, it may be a simply supported beam or it may be a overhanging. Let us consider a beam. So if it is subjected to a moment, or you can call it, if it is subjected to a couple like this, if it is subjected to a moment like this, then its shear force diagram will look like this. Its shear force diagram will be like this. These things we have discussed already in the previous videos. Its shear force will be constant, or it's better than constant. It is zero. It is zero, and you can see bending moment look like this. Bending moment will be like this. This will be the bending moment diagram. 0, 0. This is the shear force diagram, SFD, and this is the bending moment line. 0 to M, 0 to M. So a beam is said to be under pure bending when there is no shear force. Then only we can call it as beam is under pure bending. Let's derive an equation for Euler-Bernoulli's beam theory. Before that, we'll look at some assumption which we have made before we derive the equation. So the first assumption is the material of the beam is homogeneous and isotropic. Whatever the material we use for the beam is homogeneous. What do you mean by homogeneous here? Homogeneous in the sense material has same property in all the location. What do you mean by isotropic? What do you mean by isotropic? Isotropic in the sense the material has same property in the all the direction. For example, if you have a material, if the property, so for example, if the property of this material is even here, here are some in this entire material, if the property is same in all the points, in the all the nodes or on the all the location, then we call it as homogeneous material. So what do you mean by isotropic? Isotropic in the sense in a material, let us consider a material. If you consider a location where the material properties are same in the all direction, then we call it as isotropic material. So this is what is the difference. This is exactly the meaning of the homogeneous and isotropic. I hope so it is clear now. Next, so whatever the material we consider here, it is homogeneous and isotropic material. Next, second assumption is the Young's modulus. The Young's modulus E is same in compression, as well as in tension. So whatever the Young's modulus we get for each material, it will be the same for compression and tensile. In the other sense, you can say the material property, like if this is a beam element, if it is subjected to a loading like this tensile loading, and if it produces some strain, then Young's modulus will be stress by strain. I hope so you know this. Similarly, if the same bar element, if it is subjected to the compressive loading of same intensity, then its Young's modulus is stress by strain, and these two are same. In the other sense, Young's modulus for this material, if this material is subjected to tensile loading or compression loading, the Young's modulus will be the same. This is the second assumption. For some material, it won't be the same, but here we are assuming that the Young's modulus is same for compression as well as for tension. So this is our second assumption. The third assumption is like stresses are within the elastic limit or within the plastic proportional limit. Sorry, stresses are whatever the stresses which developed here. Stresses are within the proportional limit. In other sense, we can call it as like the material which we use or the material which we consider for a beam should obey the Hooke's law. Fourth assumption, what we have, the beam is under pure bending. In the sense, there is no shear force which is subjected to beam. Completely the beam is under pure bending. There is no shear force. Next, the fifth assumption which we have for here is the transverse section remains plane after bending. All the transverse section, all the transverse sections remain plane after bending. What exactly it means? Like for example, if you have a beam like this, if it is subjected to a pure bending, before bending, if it was the transverse section, or you can call it as this is the plane before bending. After the bending of this beam, this beam will be like, we will have a beam like this. So this will be the beam after bending. So this will be the earlier plane which we have. This is the plane which we have, earlier plane. For example, this is plane AB. Now after the bending, this plane AB has been shifted like this. It has been shifted like this because the inner fiber, these are the inner fibers are subjected to compression and outer fiber are subjected to tension. So this will be the plane. Like earlier this was a plane like this, and now after bending the plane is straight. So what it means in the sense, the transverse section remains plane after bending. Earlier it was plane here, earlier it was plane, and after the bending it was plane here. So transverse section won't change after bending. That was the assumption. But usual practice, what happens after bending? After bending, it look like this. Usually, it look like this. If it was bent, if the beam was bent like this, the beam was bent like this. If this was the earlier plane, after bending, it may look like this. Like it may be like this. Here it was linear, here it was non-linear. So sometime it may be happens non-linear, like a transverse section, or you get a non-linear stress distribution. Here the stress distribution is linear. Here the stress distribution was linear. So here you get a linear stress distribution, whereas here you get a non-linear stress distribution. Here we get non-linear stress distribution. That's why what we assume, all the transverse section remains plane after the bending. Next, the sixth assumption, what we have, the sixth assumption, beam is initially straight and bends into a circular arc. Beam is initially straight, beam is initially straight, it was initially straight and bend into a circular arc. So according to this assumption, if you see, earlier the beam was straight, and it is subjected to the moment. When it is subjected to pure moment or pure bending moment, then it bends into a circular arc. It bends into a circular arc. Circular arc in the sense it look like this. This will be the inner fiber. This will be the outer fiber or outer layer. So this has O. This was the neutral axis, neutral layer. This was the radius R. So beam initially it was straight. When it is subjected to movement, the bend into, like it bends like a circular arc. It bends in a circular arc. In the sense exactly it look like a circular arc. It look like an arc. In the sense, if you draw a circle, it will be like this. So it bends with a like a circular arc. This is the assumption which we have. This is the sixth assumption. Next, the seventh assumption, cross section of the beam is symmetric about the plane of loading. Like the cross section of the beam will be always symmetric about the plane of loading. This was the seventh assumption. Now we'll start with the bending equation. Like to derive the bending equation, let us consider a beam. Let us consider a beam. Suppose this was a beam, and this was the beam, and this was the neutral axis, or you can call it as neutral layer. This was the neutral layer. So as we know that a beam is made up of number of layers. A beam is made up of number of such layers. So we consider a beam, and it has number of layers. In that, this was the neutral layer. In this beam, we will consider a very small element. We will consider a small element. We will consider a very small element. If I draw very small, you won't be understand. It will be a very small element in this beam. Let us call it as A, B, C, D. Like this was a small element in the beam. Again, what we do, we consider a random layer. We consider a random layer. So let us call this is a layer which is at a distance of y from the neutral axis. Let us call it as EF. The layer is EF. Let us call this layer as EF. Now, when you apply the when it is when this beam is subjected to the pure bending, when this beam is subjected to pure bending M, when this beam is subjected to pure bending M, what happens? The inner fiber will undergo compression, and outer fiber undergoes the tensile. Outer fiber subjected to tensor and inner fiber undergoes the compression. It look like this. The beam will look like this. This is the inner fiber. This will be the outer fiber. This will be the neutral layer. This will be neutral layer. And the small element which we have here, the small element, like earlier we have this small element ABCD. Here this AB, this layer, upper layer or inner layer, it undergoes compression because of this bending. Because of this moment, this AB gets into compression, in the sense the length of AB get reduces. So the length of AB get reduces, whereas the length of CD get expands. The length of CD get expands. This is CD. This is our element after bending. Or you can call it as A dash, B dash, C dash, D dash. This is the small element which we have considered. And here we have considered the one more layer, which is EF. EF, it has been like EF. This was the layer EF. It has been undergone the tension in nature. Like this layer undergoes in tension. Like it is at a distance of y here. Clear? Like what we have done in this derivation, first we consider a straight beam. In this beam, we consider a neutral layer of the beam. Then if for deriving the bending equation, m by I is equal to sigma by y is equal to E by R. First what we do, first we need to derive this equation, this relationship, then we'll derive this relationship, then we'll derive this relationship. So to derive this relationship, sigma by y is equal to E by R, first I should know what is the strain in the beam. If I know the strain in the beam, from the Hooke's law, I know Hooke's law, from the Hooke's law, stress by strain, I can calculate the stress. So how to approach this derivation is, first I need to calculate the strain in the beam. First I need to calculate the strain in the beam. Then I need to apply the Hooke's law. From the Hooke's law, I'll get the stress. So this is what the approach to derive this equation. First, what we have done, like we consider a straight beam. In that we consider a small element. Why we have considered small element? If I know the strain in the small element, if I integrate throughout its length, I'll get the strain in the whole beam. That is the reason I have considered a small element of ABCD. In this element, I have considered a layer EF. which is at a distance of y from the neutral axis. Then I applied the moment. After the application of moment, the beam is bent like this with O as center, and this will be the radius. This will be the radius, or you can call it as radius of curvature from the neutral layer. This is the radius of curvature from the neutral layer. This beam has it look like a arc, like as we have seen the sixth assumption here. Beams bend into a circular arc. Beam will bend in a circular arc. Clear? So the inner layer will subject it to compression and the outer layer will subject it to tension. The inner layer, the length of the inner layer get contract, and the length of outer layer get expands because of bending. So this will be A dash and B dash will be the inner layer. The outer layer will be C dash and D dash. This is the complete element. In this element, this was the assumed. This we have considered a element here EF, a element EF, and after the application of moment, this will be E dash F dash, which is in its length has been got increased because of bending moment, because of this moment. Now we need to calculate the strain. With the help of strain, I can calculate the stress by using Hooke's law. So how to calculate strain? First we'll calculate strain of this, like strain in, I can write strain in layer E dash F dash, or you can write strain in the layer EF, strain in this layer. What is the strain we got in this layer? So how to calculate the strain? Strain is nothing but you can write epsilon. Strain is nothing but epsilon, which is nothing but change in the length by original length, or change in the dimension to the original dimension. So here, what is the change in the length? What is the change in the length? Delta L by L. What is the change in length? Change in length nothing but final length minus initial length divided by original length. So what is the final length? The final length of this layer is E dash F dash. Is that E dash F dash is the final length minus what is the initial length? Initial length is EF, and what is the initial original length? It is EF. See here, this is the final length and this is the original or initial length. So from this we got this equation. This is nothing but strain in layer EF, strain in layer EF. Now I can write from this figure, if you see, EF is equal to, let us call this as neutral layer or neutral axis NN. This is, let us call this as neutral layer NN. So EF is nothing but EF is equal to NN, because length of this layer EF is equal to the neutral layer NN within this element. So I can call it as EF is equal to NN. So if I substitute here, I get a strain in EF is equal to E dash F dash minus here I get NN. NN in the sense neutral layer N. Now I need to determine E dash F dash. How to determine E dash F dash here? If you see here, like how to determine like E dash F dash. To determine the E dash F dash, in the sense I need to determine what is this E dash F dash. So I know if I want to calculate, this was NN, right? This was NN. This is the neutral layer. This was the neutral layer NN. If I want to calculate NN, how I can calculate? If this was the, if this element was deflected with an angle theta, if this element was deflected with the angle theta, if I want to calculate this NN will be R into theta. This will be the R, this will be R, this will be the R multiplied with the theta will give you this NN. So I can write R into theta will be NN. R into theta will be NN. If I want to calculate what is this E dash F dash, if I want to calculate the value of this one, I should know what is the radius. The radius is it is located here, right? So from here to here, what is the distance here? It is till here it is R. This was Y. So R plus Y into the theta. It will give you the EF. So if I substitute these values here, EF is nothing but R plus Y theta minus NN is nothing but R theta divided by R theta. So it will be like Y by R. If you simplify, you'll get Y by R. The strain in the layer EF is nothing but Y by R. Strain in the element is Y by R. So next we'll go with now we got the strain. By applying Hooke's law, I can calculate the stress. I know what is Hooke's law. Hooke's law is nothing but stress by strain. Stress is directly proportional to strain within the elastic limit is known as Hooke's law. So Hooke's law is E is equal to stress by strain. So I need to calculate what is the stress. Stress is equal to Young's modulus into strain. What is strain here? Young's modulus into what is strain? Strain is nothing but Y by R, which is nothing but Y by R. So I can write this as sigma by Y is equal to E by R. Sigma by Y is equal to E by R. This is my first part of the derivation. Sigma by Y is equal to E by R. So next part, the next part of the derivation is we need to calculate we need to build the relation between bending moment and moment of inertia with respect to stress and the distance from the neutral layer. This relation I need to establish. To establish this relation, let us consider a general cross-sectional area. Let us consider usually beams comes with I section, T section, rectangular section, but we'll consider a general cross-sectional area like its neutral axis. Let us consider this as its neutral axis. So this will be its neutral axis. Let us neutral axis NA. So if I want to calculate what is the moment of inertia of this entire area, I should know the force and I should know the distance. Force into distance will be give the moment, and the resistance to the moment is nothing but inertia. If I want to calculate moment and moment of inertia, I should know force and distance. For this, what we do, we can't calculate directly for this entire area. For this, what we do, let us consider a small area here, very small area. The small area will be like its area will be dA. Its area is dA, and it is at a distance of y from the neutral axis. It is at a distance of y from the neutral axis. Now, the moment applied to this small area, the small moment applied to this small area is nothing but force into distance. Distance is from the neutral axis, it is y. Clear? Now, as we know that stress is nothing but force by area. So since it is a small element, we can call it as the elemental force divided by the elemental area. So I can write here elemental force is equal to stress into dA. So this I can substitute here. The moment is equal to df as I can write sigma into dA into y. Sigma into dA into y. Next I can write, what is this sigma? This sigma, if you see here, sigma is equal to E into y by r. Sigma is equal to E into y by r. I can substitute here. So if I substitute here, dm is equal to sigma. What is the value of sigma? E into y by r into this dA into y. Now I need to integrate throughout this area. Then I can calculate. I can get the moment of this entire area. So if I integrate this, I'll get moment is equal to E by R. Why E by R? E by R is the constant values. Young's modulus is the property of material and R is the radius of curvature. Then here if you see y into y is y square. So y square, here we go y square into dA. This will be y square into dA. This y square into dA is nothing but y square into dA is nothing but it is the moment of inertia, or you can call it a second moment of inertia. Second moment of inertia. So I can write here m is equal to E by R into integration of y square dA is nothing but I. Integration of y square dA is nothing but I. So I can write m by I is equal to E by R. M by I is equal to E by R. This is the second equation. By combining first and second equation, I get this. M by I is equal to sigma by y is equal to E by R. So this is the bending equation for beam or Euler beam theory equation. I hope you understood the derivation. If not, you just send your doubts to this mail ID so that I can respond your doubts. Samir_me@ccap.org. So if you find any difficulty in this derivation, you can mail here so that I can I can clear your doubts. Thank you for watching.